was 4.1. The topic of 4.2 is, let's get rid of earbuds, should be all gone, please. I don't want to see any earbuds out there. Is going to be doing the same stuff, but with a 3x3 system. Okay, so really there's three parts of this. If you had to break down what we're going to do today and tomorrow, we're going to represent, first of all, we just want to represent linear equations in three variables. Like, what does that mean? How would we graph something, a linear equation in three variables? Because that's new to you guys. You've never done that kind of stuff before. Once we get past that and we kind of wrap our heads around the idea of what is a linear equation in three variables, what does that even look like? Then we got to look at what would solving a system of three equations in three variables look like. I mean, what does that mean graphically? Okay. And then finally, we'll just get down to the nitty-gritty of just how do we tackle solving linear systems in three variables algebraically? What's the algebra look like? What do we have to do to get answers? We will eventually look at all this stuff. At the end of the unit, we'll look at ways we can do all this stuff using technology also. And there are some good shortcuts that allow us to solve linear systems, even really big linear systems, bigger than 3x3 linear systems using technology. We can do it really quickly and efficiently, but that's for later. All right, so first things first, let's look at something like this, representing linear equations in three variables. So if we have a linear system in three variables, our variables would be probably x, y, and z. Let's just look at maybe an equation, a linear equation in three variables. We know how to deal with a linear equation in two variables. Like if I wanted to graph this equation, what could I do? I could move the x over. That'd be fine. I could put this into, one option would be to put this into slope-intercept form. Y equals negative 5x plus 10 to graph it. That's absolutely fine. I'm actually going to not do that this time, not because it's not a good idea, but simply because I want to model what we're going to do for a linear equation in three variables, and that would not be to isolate a variable. So how else could we do this without rewriting it in slope-intercept form? We just need 2 points to graph the line. What would be two easy points to find? There you go, the y-intercept and the x-intercept, right? We could do something like, we know if I want to find the x-intercept, what's my strategy for doing that? Set y to 0, exactly. Okay, and there's our cover-up trick, where we can do, I can just cover up the y term and solve. And what's x equal to? 2. All right, so we get x equals 2. If I set x equal to 0 to solve for y, I just get 10. Whoops, and there's my 2 points. And I would just, connect and extend, and I got a line. No big deal. Okay. Well, we're maybe going to do something like that for a linear equation in three variables, but it starts to get more complicated because, first of all, if we're going to graph a linear equation in three variables, we need to extend from a two-dimensional plane into a three-dimensional space. And we've talked a little bit about this already, right? Where we have to add this third axis that's perpendicular to the other two, right? And the only place we have room to do that in our three-dimensional universe to make three mutually perpendicular vectors would be if one of them is coming straight out of the board, right? And that gets a little bit weird. So, we've got to start to think about, what does a linear equation with three variables even mean? They're so hard to graph that I'm going to rely on a cheesy video to do the work for me.